Okay, folks, I'd like to get started. Dr. Horvath is alive and well in his office. The surgery went quite well. Cancel the party. But he's a little bit sore, so he got me today. The end of class yesterday, a couple days ago, Dr. Horvath suggested that you guys take a look at bonus quiz 2 from summer 2011, particularly question number 2. That deals with the dissolution of calcium carbonate by the acid attack of ammonium ion, H4n+. Now, what you guys did last time around, S last class, you got 4.2 times 10 to the minus 3 by assuming that S was equal to the calcium ion concentration, also equal to bicarbonate and ammonia. Now, it's our job today to test this value against a rigorous analysis of this equilibrium. Now, I understand, take a look at that quiz, a lot of numbers thrown at you, a lot of terms, a lot of symbols, a lot of algebra. Now, I'd like to stay away from the algebra because we could spend the entire class today doing it. Algebra is up to you guys. What I want to do, get us through the mass and charge balance derivation, talk about plugging values in for hydronium ion, testing them, and figuring out just how good our assumption was the other day. So, those of you that has copies, I recommend that you follow along. Those of you that don't, all of the pertinent information is up on the board. So, for starters, we have this equilibrium, calcium carbonate and ammonium ion, giving us calcium ion, bicarbonate ion, and ammonia. This is our K value. Should have that written down from last time. We evaluated it, 7.2 times 10 to the minus 8. It seems as if this reaction is ineffective. Follows we have a small s value. Now, our first consideration is to start with mass balance. I know that I've got 1 molar ammonium chloride, which means that the net sum of my ammonium and my ammonia has to equal 1. That's going to come in very important. We wouldn't be able to solve the problem if we didn't make that pretty simple conclusion. So don't leave the easy stuff out. Now, we want to talk about S. S is what's of importance to us. We want to know, can I dissolve calcium carbonate very well by adding this ammonia? So S is going to be my calcium ion. I know that calcium ion is inert with respect to the chemistry that we've done thus far, so I can call S equals calcium ion. I know, though, my carbonate ion is going to undergo some Bronsted-Lowry chemistry to give me some combination of carbonate ion, bicarbonate ion, and H2CO3. I make a little question here. Are all these relevant? Well, probably not. We know that from our analysis of a lot of carbonate-containing systems that oftentimes we can simply cross one of these out. Now, as we go along, we'll find we actually can, but we'll get there in a little bit. So, is everybody okay with our mass balance? Or forever hold your peace? Okay. Now, the next step is to do charge balance. Charge balance can be a little bit more challenging for students. I'm not sure why, but we'll go right through it. All of our positive species, net sum, have to equal the net sum of all of our negative species. So, let's see here, where were we? There we are. Positive species, hydronium ion, ammonia, twice calcium ion. Remember, calcium ion is 2+. It needs to be counted twice because we're talking about the charge, not just the material itself. Charge is what matters. Equal to concentration hydroxide ion, bicarb ion, twice carbonate ion, again doubly negative, and chloride ion. Okay. Now this is where things got a little tricky for a lot of people. I remember grading this quiz. This was my second time ever teaching for Dr. Horvath. A lot of folks ran into trouble getting rid of chloride ion. A lot of people found too many variables and they included this one. But chloride ion, guys, remember, is just equal to 1. Ammonium chloride is going to dissolve completely in this solution, leaving me a 1 molar concentration of the Bronsted-Lowry inert chloride ion. So, what we can do now, we can go on through. Hydronium ion, okay. Ammonium ion, okay. Twice calcium ion, well, looks like I can start to kill some variables here. I know that calcium ion is equal to the net sum of carbonate, bicarbonate, and H2CO3. Twice calcium ion, twice carbonate, twice bicarb, twice H2CO3. Is everyone okay with that? We're just distributing through that too. Okay, so that's how we get here. Now guys, I could call this a charge balance equation because I did derive what I just wrote down from charge balance. But it's not exactly charge balance. Someone said before, they made the comment, well, H2CO3 is in there, it's not charged. At this point, though, we don't care, because I've set up several equivalencies that I'm going to use to start killing variables. So this one right here, this is the only real charge balance equation. Everything else is just derived from it. So it's okay to have H2CO3, because I'm not really doing charge balance anymore here. Which is why Dr. Horvath gives these things sort of crazy looking things. You got a star, you got a pound sign. Want to make sure that this is CB. The one below it is not. Okay, so now we'll go over to the right-hand side of the equal sign here. Hydroxide ion, bicarbonate ion, twice carbonate ion, and right here I just have +1. Corresponds to my chloride ion. Just get rid of it. No longer needs to be a variable, it's just a number now. So is everybody okay with that step? Just making a couple of exchanges there. Okay, good. Now we'll keep chugging through. What do I see here? Twice carbonate on the right. Twice carbonate on the left. We can just cross them out, because all we're doing here is math. Yeah, we know it's chemistry, but all the rules still apply. I see 2HCO3 minus, 1 bicarb here. Get rid of my 2, get rid of my bicarb on the right. I got hydronium ion here, got hydroxide ion there. Well, I know I can express one in terms of the other very, very easily through one of our fundamental relationships, Kw, hydroxide ion times hydronium ion. I'll kill hydroxide. Call it Kw divided by hydronium. Nothing too special there. Just a lot of little steps bringing us closer and closer to our conclusion. Now, this value of 1, that's special to us. Our very first mass balance consideration. Ammonium and ammonia, which is not charged, I don't think. I'll replace that 1. Now I'm in a position to use a combination of Ka and Kb values and 1 Ksp for calcium carbonate to give me an equation that has but 2 variables. So I can speculate on one, solve for the other. Compare it to the K value that I've got written up there, 7.2 times 10 to the minus 8. This is the way we've solved these problems, only the equation's a little bit longer. Stakes are a little bit higher. So, we'll go on through converting star to hashtag. I didn't even mean to say that. Generational gap. Anyway, hydronium ion, we'll just pull it straight down. We see sort of a mess here. Where the heck does this come from? All right. What I can do is I can use KaH2CO3, Ka bicarb, and KSP calcium carbonate. What these 3 Ks do is they relate all of my carbonate-containing species to the concentration of calcium ion. You just have to go through, do the rigorous algebra there. Dr. Horvath delineates it a little bit more clearly on your quiz. I'll leave that up to you guys to figure out. Again, this is just algebra, going from here down to here. I don't want to spend too much time on that today. If you guys do struggle with it, get out one of us. We'll be happy to help. But for now, we'll just have to take that as a given. So, once again, derived from Kas for my carbonate-containing species, relating that to calcium ion, I can completely eliminate any carbonate-containing terms from my equation here. Kw divided by hydronium ion over on the other side. We like that. Then I can take this ammonium and ammonia and convert it to this term here by using Ka for ammonium. And also, once again, this simple but paramount equivalence of ammonia, ammonium equals 1. Ammonia and ammonium equals 1. So this is the equation on which we'll be working. Dr. Horvath reorganizes it for you on the second page of his key to solve it for calcium ion. Once again, that's just algebra. I didn't even write it down. As a matter of fact, you can solve that for calcium ion in just 3 steps, I think. It's not too difficult. So once again, take a close look at the algebra by yourselves. If you do struggle with it, we're always happy to help. But now I want to get to the exciting part. Last class, S. 4.2, yes, question.
On your hashtag equation what happened to the ammonium atoms on the left side, equal sign?
Let me see here. Oh, excuse me. Right over here. I skipped one step. There we go, that's where it goes. Just disappears. Any other questions regarding the equations? Sure.
So even though they cross out, you're still going to use the Ka or the ammonium?
Sure. Because it still pertains more or less directly to the concentration of H3N. And remember, I can relate one to the other right here. Yeah. Another question.
And then why is the Ka ammonium, why is it hydronium plus 5.6?
That all actually falls out of the algebra. What you're going to have to do is you're actually going to factor out a term of H3N. So once again, that's all algebra, and you do find that when you go through this, you'll find a term of H4N plus equals 1 less H3N, and then you're going to end up multiplying that by Ka, so you're going to have 2 terms that contain 5.6 times 10 to the minus 10 there. We can go through it rigorously later. You can shoot me an email and we'll derive that, but that's just a 3-step or 2, I think. Okay. If we're all set, take a look at S that we got from last time. 4.2 times 10 to the minus 3. We think that's at least pretty close, but again, that's making an assumption that calcium ion equals bicarb equals ammonia. That's assuming that the gang up factor is not of consequence here, if you remember from last time, the Muhammad Ali factor. Love that story. First thing that I'm going to try. Hydronium ion, 1.0 times 10 to the minus 7. Even if I had no clue regarding pH, that's the place to start. However, sort of gee whiz pH for this is going to be pretty close to 7. Once again, you just have a weak acid and a weak base. Small extent reactions. So we anticipate hydronium ion to be pretty close to 1.0 times 10 to the minus 7. Now what I do, I plug that value in here. I solve that for calcium ion. Get my calcium ion concentration. Go through all my other equivalences. Solve for my other variables. You're always going to go back to K. Get calcium ion. The rest falls out. And we hope that we get 7.2 times 10 to the minus 8 or something real close to it. So if I try hydronium ion equals 1.0 times 10 to the minus 7 pH 7, I get K equals 5.3 times 10 to the minus 8. Pretty close. Not bad. But we can probably do a little bit better. All right, I know I see some carbonate ion floating around here, some bicarb ion. I got weak bases here. Maybe my pH is basic. 6.0 times 10 to the minus 8, that's pH like 7.2. Very mildly basic. Whoops, I went the wrong way. Go through and solve that, you'll get 2.6 times 10 to the minus 8, which tells us that's not the right way to go. pH for this system is acidic. And as a matter of fact, true hydronium ion concentration, 1.2 times 10 to the minus 7 to 2 significant figures. You can't get any better than that. with the information given to you. Of course, you could drag this out, do a little bit better had Dr. Horvath included a couple extra zeros after the decimal point, but you can stop right there. Gives us an S value of 4.37 times 10 to the minus 3. Remember, S is equal to our concentration calcium ion. Let's compare these two. Well, pretty close. We do realize that our first approach was incorrect. Even out to our few significant figures, was incorrect, but it was close. Because what happens here, guys? A little bit of the gang up factor. So I know that as one of these concentrations increases, the other one has to decrease. So that's what allowed our S equals calcium ion equals bicarbonate equals H3N to get us close to the right conclusion, because these two species depend on one another, according to the gang up factor that we'll talk about right here. So by coincidence, we were close here. However, our assumption was invalid. And the only way to do one of these is to solve it rigorously. So there's S. There's the chemistry on how to get there. Again, I recommend you guys go through the mathematics yourself. The algebra can appear to be challenging at first. Chug through it. Use the chemistry that you know, and you'll get there, I promise you. So does anyone have any questions regarding how we got all the way down here from all the way up there, before we go over the gang up factor? Okay, gang up factor. H2CO3. According to my acid-base table, H2CO3 should be a very low concentration here, because the reaction between the reaction between ammonium ion and bicarb ion is a small extent reaction. That means I should have practically none of this stuff. You can see the concentration is actually quite low. I go through KaH2CO3. This is my pH of this system. 1.2 times 10 to the minus 7. Well, derived from pH. Excuse me. This is my concentration hydronium ion. This is my concentration bicarbonate ion. I can solve one equation, one variable for H2CO3. Gives me 9.7 times 10 to the minus 4. Seems small, seems unappreciable. But in this case, if I go through and do some percent ionization, my derived species, H2CO3, divided by my initial concentration of carbonate ion, correspondent to S, 4.37 times 10 to the minus 3. That's where we get that number from. Carbonate ion initial. Times 100%, 22%! Exclamation point. The gang up factor works. We killed Muhammad Ali. 37 of us died. So, in this case, this is further proving to ourselves that once we solve for one of these variables correctly, the rest of them all fall out. Regardless of where we see them in K, well, it doesn't have to be in K. I can still solve for it by using another fundamental relationship that relates bicarb to H2CO3. Similarly, how would I get the concentration of carbonate ion in this solution? What's a good way to do it? I can think of two ways right off the cuff. Why not KaHCO3? Ka bicarb. At the same rate, why not just KSP, calcium carbonate? I know I've got concentrations for hydronium ion and bicarbonate ion. I know I've got concentration for calcium ion. I could use either one of these. You go through, you'll find carbonate ion is extremely, extremely tiny. Goes back to here, where I realize that in the vast majority of systems that we study containing carbonate ion, only 2 of these 3 species are of concentrations that would be of consequence for us. It's going to be a really small number. Leave it to you guys to take a look at that one. Simple KSP, simple KA calc though. All right. So let's see here. That just about does it for question number 2, bonus quiz 2, summer 2011. Any questions on this stuff before we hit the book? Yeah.
Did you just use KD carbonate ion for that one, or no?
Love it, sure. Any other questions?
Where did you get the value for
HCO3. This was done by, well, I just pulled it off Dr. Horvath's key, to be honest with you. But you can spit it out. Once you go through here, you have both hydronium and calcium ion, and you just work your way back up to solve for all the other variables.
Okay.
Yeah, so this is solved for by the due process of algebra. Any other questions there? Okay, so I'd like to hit the book. We're going to start. Page 1916. We're considering a new calcium salt, new to us anyway, calcium hydroxide, dissolving in water to give us component calcium ion and 2 equivalents hydroxide ion. All right. Let's see here. We're given pH equals 12.6. We realize that some of this is going to dissolve. It's going to dump the strongly basic hydroxide ion into solution, thereby increasing pH. All right. Now what we're interested in doing is perturbing, that is changing or bothering this equilibrium by doing a bunch of different things to it. Adding different ions, adding salts, adding precipitators, adding water, acids. See how they all work out. All right, let's see here. So what I'll do is I'll go ahead, write a miniature version of Horvath's table there. Applied change. Amount calcium hydroxide, that is the amount of solid stuff that we have in the bottom of the beaker. We understand this is a saturated solution. You have component ions in equilibrium with the solid. Amount calcium hydroxide is just the amount of solid stuff that we have in the bottom. And of course the concentrations of our component ions. Calcium 2+, and hydroxide. Now guys, if you could, you won't see this in your book. Add a 4th column to the right. Just write net reaction. We want to talk about whether this thing is going to go to the right, to the left, or no direction at all. Equilibrium not changed. So our 4th column, I'll just write R, X, N, short reaction. Okay. So our first change, add 1 molar sodium hydroxide. Amount of calcium hydroxide, what do we think? Increases, okay. Amount of calcium ion in solution decreases. Concentration hydroxide ion. Dove factor. The net reaction to the left or to the right? Thousand points off or whatever. This reaction is going to be pushed to the right. We're precipitating calcium hydroxide. You guys already told me that. Did I say right? I meant left. 1,000 points off. Reaction goes to the left, excuse me. You guys told me right at the very beginning we're going to precipitate calcium hydroxide because I'm adding a large concentration of a precipitator of this salt. So is that okay? Reaction to the left. Alrighty. And if you want to write a reaction equation, you can see Dr. Horvath has that one written down for you, calcium plus hydroxide to make calcium hydroxide. The opposite of the reaction we have written here. All right. I didn't realize he had already done that for you guys. I was stoked that we nailed those first three. All right. Next question. What do we got here? Add 1 molar calcium chloride. Once again, a similar situation. So we'll ask, amount of calcium hydroxide solid? Increases. Concentration calcium ion? Sure it does. Calcium chloride, very soluble. Concentration hydroxide ion? Decreases. And the reaction goes? Perfect. So once again, if we add a precipitator, either hydroxide or calcium ion, we realize the result is going to be the same. I precipitate out calcium hydroxide. However, if I add calcium ion, naturally, my calcium ion concentration is increased. Vice versa for sodium hydroxide. Any questions there? Just saying if we add a precipitator, we're going to precipitate. All right. A little bit more exotic now. Let's add 1 molar hydrochloric acid to this solution. So what do we think is going to happen? Amount of calcium hydroxide solid? Decreases. We've been talking about this for a little while now. If I have an acid attack on a basic anion for a semi-soluble salt, it's going to become more soluble. I'm going to dissolve some of my calcium hydroxide, thereby increasing, of course, my concentration of calcium ion. What do you guys think about the concentration of hydroxide ion, though? Decreases. It's gotta. I'm putting a strong acid into the solution. So, under your reaction column, we got a new one. I don't see hydronium ion anywhere here. I'll have to write down a reaction that corresponds to calcium hydroxide reacting with hydronium to give me component calcium ion and what? Water, exactly. No hydroxide ion to speak of in that new equation. So we'll go ahead and we'll jot it down. So that's our new reaction. Calcium hydroxide reacting with 2 equivalents of hydronium ion to give you calcium ion and not hydroxide ion this time, because remember, hydronium hydroxide murdered liquid water. Now, what's that? Oh, yeah, I think so. Thank you. So any questions on why we wrote down what we did here? Okay. Now here we want to give a nod. Same bonus quiz that we were looking at before. BQ2, Summer 11. If you look at question number 1, Dr. Horvath has you guys analyze, had those guys analyze a situation like this one. Now, for those of you that might not have a copy available to you, I'll read quickly the question, and we'll talk about what the answer is and why. Consider treating 1 mole calcium hydroxide solid with 1 liter of 1 molar HCl. How must resultant system pH and the solubility of calcium hydroxide compare to the pH and the solubility of calcium hydroxide in pure water, and why? Okay, we already told ourselves concentration hydroxide ions going down. pH has to be lower. I'm adding an acid. That should be apparent. Now, what am I going to be left with after I add my hydronium ion here? I'm left with a significant concentration of calcium 2+, a precipitator of calcium hydroxide. So this equilibrium is actually going to be pushed to the left once all of my strong acid has been consumed. Because what I've done is I've destroyed some calcium hydroxide. There's still some solid left over though. This equilibrium still exists. However, I've got appreciable calcium ion now. As a matter of fact, if I wanted to consider this reaction, once I've reestablished an equilibrium, it's going to lie further to the left. It's an important point to realize. Just because I add a strong acid doesn't mean I render calcium hydroxide more soluble. Just because I murder some of it doesn't mean that this equilibrium disappears completely. This is, of course, dependent on the amount of hydronium ion that I add. If I add enough to kill all the calcium hydroxide, this goes away, the reaction goes all the way over to the right. But that's only if I add a true excess of hydronium ion. Again, take a look at that quiz. Make sure that makes sense to y'all. Dr. Horvath does it by the numbers. We'll do it by the concepts, so we can get through and maybe practice a couple complex Ks. Any questions there? Adding an acid, kill some calcium hydroxide, end up pushing this equilibrium to the left though. Okay? Next change. Add some solid calcium hydroxide. Some of this is filled out for us, but we'll do the rest. Amount of calcium hydroxide. Of course. Concentration calcium ion, hydroxide ion, no change. Horvath gave that to you. It's important to remember, if I'm putting a solid in to an equilibrium such as this one, if I put more of my solid in, I won't be lazy about phase labels here. Calcium hydroxide solid doesn't show up anywhere in any equilibrium expression. Should never. So if I just add some more of the solid stuff, by definition, it's not going to change my equilibrium. Reaction, no change. All right. Next concern to make. We'll add some water. What happens when I add some water to this? What am I going to do to calcium hydroxide? Decrease. I'm going to dissolve a little bit more of it. Concentration calcium ion hydroxide ion. I think there are two possible answers, and I don't think increase is one of them. Depending on the amount of water that I add, no change to decrease on both fronts. Now, why is that? If I keep adding water to this solution, I'm going to dissolve more calcium hydroxide. I know I lose some of it. If I don't dissolve all of it, though, this is still the only pertinent K for calcium hydroxide ion. Which means there'd be no change. However, if I kill all my calcium hydroxide, if I add a pool full of water to 10 grams of calcium hydroxide, I'm probably going to dissolve it all. Then my concentrations of calcium ion and hydroxide ion are both going to change, and they're both going to go down. Do we have any questions on the concept there? It's a good one. Okay, chug it right along. We're going to have 1 molar sodium chloride. Now, if you guys remember, Dr. Horvath, maybe on Monday, maybe on Wednesday, what's the salt effect? That's what we're quizzing here. Add 1 molar, significant concentration of sodium chloride. Well, we know the salt effect is a Coulombic effect. My chloride ions are going to be attracted to the second coordination sphere around calcium. They're going to form a protective shell to prevent calcium ion from meeting hydroxide ion. Because kinetically, these two have to touch before I make calcium hydroxide. Dr. Horvath went over this with you guys earlier this week, I believe. So, I'm going to render calcium hydroxide slightly more soluble by the salt effect here. Neither sodium nor chloride ion is a precipitator of calcium hydroxide. So this is salt effect. I'll even put it in parentheses here so we remember. Salt effect. So the amount of calcium hydroxide, up or down? Down. Concentrations, calcium hydroxide. Up and up. And my reaction to the left or to the right? To the right. Because once again, this is still my pertinent equilibrium that relates calcium ion to hydroxide ion. The only pertinent equilibrium that does such. And it's going to be pushed over to the right because I'm dissolving more calcium hydroxide as a result of the salt effect. All right. So any questions on those first 7? I'd like to or on those first 6. I'd like to touch on the 7th one. That gets us into a complex K. Before that, though, I want to make sure we're solid here. Great. Okay. So now, we're going to change the game a little bit. Adding 1 molar sodium carbonate. And he gives us a hint. How do the solubilities of calcium carbonate and calcium hydroxide compare? So we'll figure it out. So I know carbonate ion is certainly not a precipitator of calcium hydroxide. It is, however, a precipitator of calcium carbonate. So if I wish to consider writing a reaction that pertains to the addition of sodium carbonate to my saturated calcium hydroxide solution, it's going to look like this. I'm going to take my solid calcium hydroxide, add to it my carbonate ion. AQ, remember, sodium carbonate, sodium salts, think soluble. These are going to be in equilibrium with calcium carbonate and 2 equivalents of my now aqueous hydroxide ion. So this quickly turns into a complex K problem, but once again, I impress on my discussion sections. Just because we say complex K doesn't mean it's necessarily hard. It just means there's more than one. There's no need to overcomplicate such problems. So, first thing that I'll do, this is question 1916, top of page 1917. Specifically, calculate K for the new equilibrium. So, want to write K here. Well, I've only got two solute species here, hydroxide and carbonate ion. Hydroxide ion, numerator. Remember the rules, we got to square it. Denominator. Carbonate ion. Well, I don't have this on my information sheet. We realize, okay, we're going to have to come to some valuable conclusion by multiplying this K by factors of 1, not factors of other K values, and we certainly can't change the number by not multiplying by 1. So, do I have any recommendations for what I could multiply by here to give me some meaningful K values for which I actually have some numbers? I heard a lot just now. Let's look at the chemistry. Calcium hydroxide, dissolving to give you calcium ion, although it's complexed here, and hydroxide ion. I have to kill, that is, I have to dissolve calcium hydroxide before I can make calcium carbonate. Similarly, if I look at this reaction going right to left, that is backwards, I have to dissolve, I have to kill calcium carbonate before I make calcium hydroxide. So what I'm going to think in my head before I even start multiplying, I want to see some KSPs. Regardless of pH, acid-base chemistry that's going on here, I need the KSPs for both of these if I'm going to do anything to this system. If I want to work with this thing, I need my two KSPs. So I'm going to pick a factor of calcium, 2 plus, top and bottom. Remember, we have to multiply by 1. I can't just put calcium ion on the top nor on the bottom. Has to be both. Numerator, KSP, calcium hydroxide. Denominator, KSP, calcium carbonate. Complex equilibria, guys. Don't make them too hard. Look at the chemistry first. Figure out what you might need. Try to make it match your needs by being strategic before you just start throwing stuff at it. Any questions on this stuff?
Does it matter what one's on the top and which one is on the bottom?
Does it matter? Absolutely. It is of paramount importance, because if I had this reversed, then I would be writing K for the reverse reaction. Because recall, as written, I dissolve calcium hydroxide, KSP, calcium hydroxide numerator, to make calcium carbonate, also a semi-soluble salt, but has to be in the denominator because it's a product. So if I read this reaction the other way, we'd have the inverse of what I have written down here. Is that all right? Okay. So guys, if you have any questions, feel free to stick around. Otherwise, have a very good break. We'll see you next Monday.